Good morning, welcome back. We're still talking about neural networks, except we're now in the last decade. To understand all the buzzwords of deep networks and why they're so exciting, you need to understand what neural networks have done for us in the prior 3-4 decades and where we were stuck and how we got unstuck. So I summarize for you again the problems with neural networks as of 10-15 years ago. Neural networks are generic universal regressors. Okay? They're universal approximators. You can use them to learn, in principle, any nonlinear function, as well as, of course, linear functions. There's something very seducing about it because you could be lazy. You didn't have to really understand the domain much. You didn't really need to figure out what the right bias is. You just throw your data at a one hidden layer network and try maybe different number of units and maybe try different step sizes or something like that. And very often, your network learned your function with reasonable accuracy and reasonable generalization. It was so successful in the 80s and 90s that there were whole conferences devoted to new applications of neural networks, and they just made their way into everything. They became like the new linear regression, except they were more than linear. But then they got stuck. And these are the reasons they got stuck. By stuck, I mean that they still were useful for simple problems, but then there were problems for which they were not useful for. One reason they got stuck is computation. Training them is very expensive. As you probably noticed in your homework, a lot of iterations, and if you do tweaking with the topology of the network, then you have to start all over again. Every time you change the number of units, you may want to start all over again. And you have to control the step size, and you may get stuck. And as the size of the problems grew, the number of inputs grew, and the number of weights grew square in that, more or less, the amount of computation grew with it. Second problem, I mentioned already, is when you try to do more complex operations, you may want to have multiple layers. What do the multiple layers do for you? They allow you to do sequential processing of the data, so that the first hidden layer extracts some intermediate computation or features from the input, and then the next layer after that extracts features of that, and then features of that, and so forth. So hierarchical computation. This is not a new idea. Our brain does a lot of things that way. The part of the brain that's understood the best in this regard is visual cortex. In visual cortex, there's work going back starting in the 50s and then becoming very strong in the 70s and 80s of understanding how signals from the retina, from the eye, make their way to visual cortex in the back of your head and into a layer called V1. And then from V1 to V2, and I think there's V1A and V1B, I mean, there's variations. And what they figured out is happening there is exactly the same as what I just described, that each layer extracts features from the layer before it. So this is a very tempting architecture for trying to do very high-level classification or recognition, like recognizing objects and images. If you try to do that, you have the computation problem, number one. Number two is, how do you get all the layers to learn if the gradient of the error with regard to each layer becomes smaller and smaller as the layer moves, as you move in the layers towards the input layer? So I mentioned that before. Here's your input layer. Here's your first hidden layer, second hidden layer, third hidden layer, and let's say you finally have an output. If you calculate the gradient of the error, of the global error, with regard to any one of the weights, you will find that the gradient with regard to these weights will typically be extremely small. In fact, they would get smaller and smaller as you look at weights here, 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 and here. This is because these gradients are effectively a product of the partial derivatives along the way, including the derivatives of the transfer function. If you remember the transfer function, that we use so far is the sigmoid. Its derivative is bounded between 0 and 1, well, actually between 0 and a quarter. There will be situations where you can change the transfer function. You can make its derivative greater than 1, right? You can just take the sigmoid function and squish it, so make the derivative around 0 even stronger. But the problem is, as long as the derivative is if it's always greater than 1, then multiplying them will make the gradients explode rather than vanish. So more often, the gradient will vanish. Sometimes it would explode. The general phenomena is that there is instability in the gradient. The gradients here are very, very different than the gradients here. In the general case, in the more common case where the gradients vanish as you go down in this direction, that means that most of the movement, most of the learning happens here. And we said that that actually doesn't make sense. You don't want to learn the high level before you learn the low level, right? The high level would be things like fuzzy, white, and black, and tongue means dog, okay? But for fuzzy, white, and black, you need to have relative understanding of what fuzzy consists of. You want to build it the other way around. You want to build first lines and angles and shapes and 2.5D objects and then 3D objects and so forth. So you don't want to start learning from the top. You want to start learning from the bottom. It's like starting to learn calculus first and then working your way down to learning addition. It doesn't make sense. So this is the problem of vanishing exploding gradients. A very related problem, these kind of go together, is learning useful internal representations. Again, if you start your learning from the top, if most of the learning is done in the upper layers first, they're based on randomly extracted features, or random features. What you really want is for the intermediate units to ideally stand for something, either by themselves or in combination. You want them to represent meaningful high-level or intermediate-level concepts from the input. I showed you an example of autonomous driving where we saw that one of these hidden units could be interpretable as representing a particular angle of the road, if you remember that, if you look at the pattern of its weights. What was known in the 80s and 90s is that in a very simple network, with maybe a single hidden layer, if you force the network to reproduce the output from the input, to just be an autoencoder passing through a bottleneck, you often get meaningful internal representations. So that was like a little tidbit. It was I was teaching this class in the 90s, and even later I showed examples of how putting, I showed it until recently actually, how putting vectors in one layer of size 8 and then forcing them to go through a bottleneck of 3 hidden units and then reproducing again those vectors of length 8 forces you to learn a binary encoding of those networks. So there are other sort of cute, fun examples of learning family relations. If you give a large training example, a large training set of how people are related to each other by different family relations, and you give demographics like their gender and their nationality and so forth, then you can show the network often learns concepts like gender and nationality and age. So sometimes it latches onto the right representation, but as you go to these deep networks, the chance of it happening go down because of the problem of starting to learn from the top. I'll talk in more depth about the last one when we talk about recursive neural networks, so I'll leave it with that. So there were a few very powerful ideas that were explored and exploited starting about 10, 15 years ago that solved all of these problems. And I think the most important one is the auto encoder that we discussed last time. And especially how the auto encoder was implemented. So the idea of the auto encoder is that you learn, let me roll back. Sometimes you could learn intermediate representations more usefully, forget about the auto encoder for a moment, by deliberately starting to train from the bottom up. So the idea is you forget about the rest of the network. You have one hidden layer only, and you train it not to recognize a dog, but to recognize edges. So you have a related task. And what you care about is these connections. And you train them to do the related task. And then you freeze these weights. Now you have a layer of useful, fairly basic, but useful features. And now you train the next layer to do another related task. Let's say recognize shapes. These would be edges. And now you're training this layer to do another useful intermediate task. And then you freeze these weights, and then you train the next level up and so forth. So you can, one problem it's solved is that you're now training from the bottom up, as you should. The second one is that you're guiding the network, you're telling it, in order to recognize a dog, you need to start by recognizing these other things. They aren't always very useful related tasks, but you can certainly try to find a simpler task than the one you're aiming for, and to train the first few layers with it. Now we come to the autoencoder. If you don't have a good idea of what would be a related task, you can still start from the bottom and train the first few layers by basically asking them to shrink the representation, or by compressing the input representation. How do you do that? In autoencoding, if the number of inputs is 10,000, you might force it down to 1,000 or even less. And you do it by setting a network with 10,000 inputs, 10,000 outputs, and only, say, 1,000 hidden units. And now you take your training examples, let's say images. You ignore the label of dog or not dog. You just ask the network to learn a mapping from every image to itself. But the trick is that that mapping has to pass through a bottleneck. Now, you may not be able to learn the mapping exactly, in the sense there would be some distortion. There would be some difference between the representation of the image here and its original representation. But you do gradient descent with the goal of minimizing that distortion. In the end, if you're successful, you've represented every image with just 1,000 numbers as opposed to 10,000 numbers. This is a form of compression. Lossy compression, but compression. Why is that good? Well, natural images and natural inputs in general have a lot of redundancy in them. So you can think of the step of autoencoding as trying to reduce that redundancy. Remember that the more you reduce the size of the input representation, the more you reduce the number of weights in the network by a polynomial factor. The more you reduce your training computation time, but more important than that, the more you reduce the expressive power needed. Learning a mapping of 10,000 to one binary output is a lot harder, mathematically speaking. It's a much larger space than a mapping from 1,000 numbers to one binary output. So if you know nothing about the domain except you know that the input is redundant, autoencoding, passing through a bottleneck, and then using that representation is a good first step. And you can repeat that step multiple times. You can go down from 10,000 to 1,000, then freeze these weights. And now treat these 1,000 as the still have redundancy. You still want to compress them further. Maybe you bring them down to 100. And then ask them to reproduce the 1,000. So now your bottleneck goes like this. So you can build layer upon layer of smaller size, but with the mapping that allows you to keep the most salient aspects of your input. So this autoencoder sometimes goes by the name of pre-training. Because if you think of training as supervised learning, as having the output that you want and doing gradient descent in that, pre-training is some processing that you do of your input without seeing the labels, without regard to what it is you're trying to learn. So this is kind of a funny way of learning. You're learning without knowing what you're going to learn eventually. And you're not really learning, you're just reducing your dimensionality. So that would be another word, dimensionality reduction. This is really the purpose of an autoencoder. Now, you don't have to use an autoencoder for dimensionality reduction. If you're a statistician and you're given a very redundant representation of input, there are other techniques that are actually better understood theoretically for dimensionality reduction. Maybe the most popular one is principal component analysis. And indeed, you could do that. You could do a variation on principal component analysis, independent component analysis, other related techniques to reduce the dimensionality of your input. Whether they would work better as well, I don't know. But the point is that this is not really part of learning. This is why it's called pre-learning. It's dealing with the problem of a typical image has a tremendous amount of redundancy in it. All right, so this is idea number one. Or I would rather call it idea number two. Idea number one is the related task. If you can think of a related task, do that. That will both do the dimensionality reduction and push you in the direction that's useful to you at the same time. If you can't think of a related task, if you don't have access to a related task, idea number two is do it without a related task. Just reduce the dimensionality. Idea number three is also inspired by the brain. I mentioned it before, I'll mention it again. If you want to learn features like circles or squares or different kinds of shapes, and you want to learn them in location invariant way, call it translation invariance. By translation, I don't mean from English to French here. I mean translation of a physical body in space. So translation invariance means you want to recognize a circle, whether it's here or here or here or here or here or here. If you want to learn translation invariance, how do you do it with the neural network? It is unlikely the network will learn it by itself unless you help it with the right topology. So if you look at our brain, if this is the visual space, any particular neuron, especially in V1 in the first layer, is only connected to a small part of that image. And different neurons are connected to different small parts that are overlapping. These are called the receptive fields. Of the neuron. If you want to learn the same function in a translation invariant way, here's one thing you can do. Build a layer of hidden neurons that each have a different receptive field. They could have overlap between them. So they could be like 10 by 10 and another 10 by 10 and another 10 by 10, and they cover the whole space. Each one of these 10 by 10s would have 100 weights. 100 weights to some neuron. Now do any kind of learning with this as your first layer, let's say auto-encoding, but do it in a way that forces these 100 weights to be identical to any other 100 weights. So if you call them W1 through W100, even though there may be, let's say, 10,000 hidden units here, 10,000 times 100 is 1,000,000. You could, in principle, have 1,000,000 different weights, but you don't. You enforce the condition that the same 100 weights are here, as are here, as are here, as are here. So you're basically only learning 100 weights. It is actually quite easy to enforce that condition. When you calculate the gradient with regard to any one of the weights, you first calculate it as if they're not tied together, but then you take the gradient for each one of weight number 20 here, weight number 20 here, weight number 20 here, and 20 here, and so forth. You average them. And that's it. Or you can go all the way to calculating the change in the weight, and then you average the change in the weight and apply to everybody. So these weights all tend to evolve together. The 100 from here will evolve exactly the same way as the 100 here. In other words, you're really learning only one function. One function of 100 weights, as opposed to 10,000 functions of 100 weights. Lots of terms that are associated with this. First of all, we'll call it weight tying. Now, once you train the network, you can ask yourself, what does this function do? The answer is this function does somewhat different things depending on where you apply it. If you apply it to this area, it extracts some feature from here. If you apply it to this area, it extracts the same feature from here. So the output of these are a function not only of what is the function that they extract, but also of where they're applied. This idea in mathematics is called convolution. A convolution of two functions is when you combine two functions with some offset between them. So this idea also goes by the name of convolution. And from this comes the term convolutional neural networks, which you may have heard. So the idea of a convolutional neural network is basically to attack the problem of translation invariance. Now, you could, suppose you didn't do that. Suppose you did not tie these 100 weights to each other. You could still ask each one of the neurons to learn a basic feature, like a line or a shape. But you would have 1/10,000th of the number of examples. If you think that there's a certain distribution of, let's say, lines or orientations in images, by not tying your learning across different translation you are allowing the unit that learns of, say, a particular orientation in a particular location to learn only from examples of that orientation in that location. Whereas when you tie them all together, all 10,000 of them, you're learning a certain orientation from examples of it occurring in any location. So you have, in principle, 10,000 times more training data. This is an example of taking a bias that you believe exists or is relevant to your task and encoding it as part of your topology, making a huge difference in constraining your search, constraining your expressive power in your search. When you process images, you may not know what is the important things for dogs, but you know that dogs can occur, the face of a dog can occur here or here or here or here or here. You do know that the answer should be more or less translation invariant. So you take advantage of it in your topology. What other things do you know when you're about to recognize a dog? What else is invariant? Size. So size is another example of something that going into images, in the very nature of what images are, usually you can see a dog that's this big or this big or that big. That's a lot harder to take advantage of. But you can imagine doing something like that with the hierarchy of layers, so that you're learning the same function lower or higher in the hierarchy. So convolutional neural networks, once they were applied especially to sort of 2D inputs like vision, and even for 1D inputs, if you think of speech like acoustics, kind of a one-dimensional a process, you can still think of learning things that are translation invariant, that could occur in multiple places. But by far the biggest winner from the idea of convolutional neural networks is image processing. And often the way they're applied is gradually and hierarchically, so you may not have a mapping, you may not have, you may have 10,000 here, so you have a layer of 10,000 hidden units here, and now you may pull them together using maybe an auto encoder to reduce their dimensionality and then apply another layer on top of that. So you can start building, so making architectural choices of what kind of convolutional neural network you start with, what receptive field each one of the neurons have, what underlying features they're going to learn, and then maybe put another layer on top of it that reduces the dimensionality. You start using these building blocks of dimensionality reduction and in translation invariance by weight tying. And these two ideas together give you a big advantage here for learning internal representations. What do we do about the gradients? The vanishing gradients. The few things that we did starting to learn from the bottom already help a lot. Because if you start learning from the bottom, you learn one layer at a time, you don't have a vanishing gradient problem. So the typical process would be you learn one layer, you freeze that layer, freeze those weights, you put in another layer, and now you train the second layer with the first layer frozen, and then you freeze that and you move on. However, you can at some point, and you should at some point, unfreeze the weights that you froze. Let's take simply a two hidden layer situation. You have one hidden layer, you trained it maybe with auto encoder, maybe with a related task, you freeze it. Then you put a second layer and you train that to produce your final outcome. And now you say to yourself, I'm now in a pretty good place. I found a good place in weight space where my error is reasonable, but I can now unfreeze all the weights and continue to do gradient descent. So this is a heuristic. You got to a reasonable point, and now you are opening up the space for further optimization. Gradient descent will guarantee, as long as you don't overfit, that you will only do better than what you're doing right now. So that would be another idea. That would be freeze, then unfreeze. Here's another extremely powerful idea. Not enough attention was put on the transfer function. The transfer function, from what we learned, should be nonlinear and should be differentiable if you want to do gradient descent. People have played for many, many years with a sigmoid. That's sigmoid. And with some variations of the sigmoids, for example, hyperbolic tangent is very similar to the sigmoid. It just goes from -1 to +1, and it's slightly different than the sigmoid. But they all share these properties of saturating at both sides, and that was considered a good thing because it was making the unit stable. Once you push the total input into one of them all the way to positive, all the way to negative, they were stable. But stability means also very slow learning, right? If a unit is here, namely in the last iteration, most of the inputs that came pushed the net to here or to here, that means the unit was saturated or stable. It was doing something very specific. It was basically creating more or less a binary distinction between two situations. But if you needed to get it out of there to do something else more useful, you couldn't do that. In addition, the kind of representations that networks were learning were very, very distributed because every hidden unit could only contribute a limited amount to the next layer. This hidden unit could contribute at most 1 or 0 to the next layer. There was no unit that could make a real big difference in the next layer, unless, of course, you multiply it by a very large weight. So typically, the way the networks, the kind of solutions networks found, relied on many, many units being saturated at 1, and the combined effect was large enough to do something in the next layer. Now compare this to this kind of transfer function. This goes on forever. And this is at 0. This is 0 here. Okay, so I'm comparing the sigmoid to this transfer function. This is a linear transfer function, really, like the one we studied first, except at some point, let's say at 0, it zeroes out. It doesn't become negative. It just becomes 0. It's not differentiable at this point. That's one problem with it. But we can fix that problem in two ways. One, we can just ignore it because the chances of us being exactly here are very small. So it is differentiable up to here and from here on. Second thing we can do is we can approximate this shape with a function that looks like this, log of 1 plus e to the x. So log of e to the x is just x. That's just a straight line. But if x is negative, e to the negative number is very small. As x becomes more and more negative, this goes to 0. You get log of 1. So the asymptote here on this side is here, is at 0. So the function looks like this. It asymptotes to this line here, and it asymptotes to 0 here. And here it's nice and smooth. And it's differentiable. And not only is it differentiable, its derivative happens to be the sigmoid function. Not important, but just a neat fact. So ignore the fact that this is not differentiable, because we could either use this or we could just ignore it and use the bilinear form anyway. This kind of transfer function is called a rectified linear unit. And that's RELU, so that's ReLU, ReLU unit. Why is it so powerful? Several reasons. It is still nonlinear, so you can use it to build, in principle, anything. The gradient doesn't vanish. What is the gradient? What is the gradient of this function in the limit? Or what is the gradient of, this is a 45-degree angle here. What is the gradient here? Give me a number. 1. The gradient is 1 in the positive side of things. And it's 0 if the total net is negative. So when you're in the learning part, the gradient is 1, which means that if you use a deep network of multiple layers and they all use these ReLUs as the transfer functions, the gradient does not become large or small. You're just multiplying by 1 all the time. That's a nice trick. Secondly, any one unit could become very, very powerful. As you drive the inputs into this unit higher and higher, the output can become arbitrarily large. It's not bounded. Whereas here, it saturates at 1. So you're giving individual units the ability to express meaningful, significant impact by themselves. They don't need to rely on multiple units. As a result, networks of ReLUs tend to develop representations that are more sparse, that are less distributed. Sparse representations are good. This is dimensionality reduction. So I'll write it here. Advantages of ReLUs. Okay, like this. ReLUs. One is gradients don't vanish or explode. This is because the derivative is 1 in the interesting part of the network. Second thing is induces sparse representations. Once these were discovered, or even before, people started experimenting with all kinds of transfer functions. Let me see what others I want to do. We talked about differentiability. We talked about, what would make a good transfer function? Well, it should be differentiable. Well, maybe in one point it doesn't have to be, but overall it should be differentiable so that you can do gradient descent. You should look at its slope near 0. Assuming you start a network with random small weights, we talked about it a lot. Most units start their life with their net being close to 0. So you should look at what happens close to 0. In this case, what happens is if you're on the negative side, you're stuck there. You know, there's no dependence on the network on the net at all. If you're on the positive side, you get pushed either to here or up. And the question is the slope. If you look at the slope here, it's 1. The slope here is at most a quarter. So you would move faster. We talked about the range, whether the unit saturates or not. This lack of saturation in ReLU is a two-edged sword. On one hand, it makes for faster learning because each unit can gain more and more influence. On the other hand, the stability of the sigmoid is lost. With a sigmoid, once the unit is saturated, it's stable. It's hard to get it out of there, but it's also hard to wreck it. So you have a trade-off here between learning efficiency and stability, which, when you think about it, we all have that problem with our own learning, and it is an inherent trade-off in learning. How much do you hold on to things that you learn versus how open you are to new ideas? If you're here, and if you're really using the sharp, not the smooth part, but the original sharp straight line there, you're stuck with 0 gradient, which means you learn nothing. Right? Anything that passes through that unit will be multiplied by the internal, the gradient of this transfer function. So basically, if you start there, you're stuck. It's not used anymore. That's not necessarily a bad thing. It would lead to sparse representations in the sense that this unit will not participate in that particular input that caused the total net to be negative. But you could change that. You could make the slope here be different than 0. It could be sort of bilinear in general, but not 0. So you can think of a bilinear transfer function as another interesting thing to explore, or bisloped. You can learn the slope itself with the parameter. You can make the slope itself a learnable thing and take the derivative of that as well, right? So remember that all the decisions we make here, some of them we encode when we start. The rest of them are open to gradient descent. So whenever you talk about features of a transfer function, the transfer function itself could have parameters that in turn could be considered subject to gradient descent. We'll see that in a minute when we talk about transistors. Yeah?
If we make the second part very small slope, will it also have the gradient?
Yes. Yes, if this is less than 1, and if you make them all in all the layers, then you will have the vanishing gradient problem. So you need to worry about the vanishing gradient. But if you're building your network from the bottom up as opposed from the top down, that's another way of finding vanishing gradient. One other idea that came out roughly together with the ReLUs is the idea of a dropout. Dropout is the idea of deliberately inducing robustness in the representation by depriving the network of different weights at different times. The way it's implemented is during training. For each training example, we randomly remove a randomly selected subset of the weights, and then do the gradient descent calculation, the gradient calculation with regard to the network that doesn't have those weights. What it means is that there's no, if you do it repeatedly over all your training examples, and every time you take out different small subset of the weights, you're basically telling the weights none of you are indispensable. You're forcing the network to find a solution that is more robust, that does not depend on any particular weight, any particular relation. Now this would tend to develop the opposite of sparse representation. It would tend to develop a more distributed representation, because distributed representations are more robust. But the extent of this dropout, how many of the weights you remove, determines how much you push. You can fine-tune it to control how much you push the network towards robustness versus how much you push it towards simplicity, towards one unit taking care of a significant amount of work. Yeah.
What exactly do you mean by a sparse representation?
A sparse representation is a representation that, for typical input, would use a small subset of the units would be active. So, it's a very good question. I kind of assumed it without defining it. Here's a hidden layer. Let's say you want to represent tail of a dog. Somehow in the process of learning the whole concept of a dog, some useful thing to learn is the tail. Now you have a lot of images. You have 1 million images, and many of them have tails in them. A sparse representation, an extreme sparse representation, would be one particular unit that would be your tail unit, tail hidden unit. It would light up, it would be active every time there's a tail in the image. And it would not be active when there's no tail in the image. It is a tail detector, okay? But it's a very sparse tail detector. The alternative, a distributed representation, would be some combination of units, maybe 2, maybe 100, depends on how distributed you want to make it, that their combined state would relate to having a tail in the image. So every time there's a tail in the image, this particular vector of hidden units would together have some pattern. It could be a specific pattern of this is on, this is on, this is off, this is on, or it could be a combination of patterns. But it would be something about this entire array of 100 units that captures a tail. There's no one particular tail unit. This is actually relates to a philosophical debate that's been going on in the neuroscience literature about, do we have grandmother neurons? We suddenly recognize our grandmother. Is there a particular neuron in our brain that fires, one particular one fires every time you see your grandmother? Something happens in your brain when you see your grandmother, but could you isolate it to one particular neuron or not? The general assumption is it's not. For high-level concepts like grandmother, of which there are many, the assumption is that it's not a single neuron. If it were a single neuron, what happens if it's damaged or dies? All of a sudden, So there's redundancy, there's robustness in having distributed representations. If you have a distributed representation, you can say that if these represent a distributed representation of a tail, it doesn't have to be an exact match. If it's long enough array, a long enough set of units, you can say that here's a stereotypical tail, but if you're off from it by 1 or 2 units, it's still a tail. So whether it's a tail or not is a fuzzier distinction, but it's a more robust distinction. If one of these units malfunctions, you still recognize the tail. Okay? So that's what we mean by distributed versus sparse representation. right, we covered most of the important developments. Maybe the most important one that's left is recurrent networks. So let's talk about recurrent neural networks. Most of what we talked about was in the context of feed-forward networks, meaning that the underlying graph is a DAG, directed acyclic graph. Now, when do we want a recurrent network? The answer is usually we would want a recurrent network when we are trying to carry something, some computation that we've done in the past for the future. And by future, I mean for the next example that we're trying to recognize or compute on. So the typical situation where we use recurrent networks is when we process sequential data, such as time series, speech, language, something that is left to right or past to future. In a typical pre-2000 situation, you have your input, could be words in a document, or acoustic signals, or temperature time series. You're trying to recognize some phenomena that might happen. Let's say you're just trying to recognize if something happened or not, and you can try it here, or here, or here, or here, everywhere. So you move a window of inputs. This is your input. Feed it into your network. And then you move it and try again, and move it and try again. This is the most simple-minded way of doing it, is a moving window. Now, sometimes you might have context that you want to carry with you. The way it was done until 10 years ago is by making connections let's say from this layer down back to this layer, or you can even draw it as like this, having an additional input here, pseudo inputs, and making connections to these pseudo inputs so that they connect to here. Somehow feeding back information that the network already calculated as input to the next position of your computation. Can you do gradient descent with this kind of a network? The answer is yes, you can. Even though it has loops in it, so you might think that the gradient is not well defined. Well, it has loops, but the loops only happen when you move a step aside. So if you think of these movements as movements in time, you can take a recursive network and make it unrecursive by opening it up in time, have multiple copies of it in different times. So the important take-home message from this is that recurrent neural networks can be learned with gradient descent. It doesn't mean that they learn useful things. They're harder to learn with, but in principle, you can apply gradient descent to recurrent neural networks. So these are recurrent or recursive neural networks. And more serious limitations of recursive neural networks is that it's very hard for them to learn something and keep it long term. By long term, I mean after moving this multiple times. You can keep what you learn and influence the next movement to here. But that's it. Then what you learn, what you compute on this window will move to help you with this window. So you can always influence time t with information you computed for time t minus 1 or frame t minus 1, but not beyond that. What was question?
Why not beyond that? Why can't you do multiple recursions?
You can. Well, no, wait a minute. Multiple recursions, what do you mean?
So like as a loop feeds back to a layer, to a layer, to a layer.
Yeah, let's say you have that, and this, and this.
But 3 time units to get back.
Oh, I see. Okay, but it would be finite. It would still be finite.
Okay,
What was missing was a mechanism for long-term memory, for keeping something, let's say in the context of language, you start reading an article about baseball, and you have some words that indicate it's baseball, and you want the network to realize it's about baseball, and then when there's further discussion that does not involve the words of baseball, you still wanted to know it's in the context of baseball. So it's a global context that you want to keep around for a long time, unless you have evidence that the topic changed, in which case you want to get rid of that context. So what these networks are in the simplest non-recursive case, they're one-time shots. They have no memory from step to step. And what the recursion gives you is limited, finite amount of memory. And what you want is unlimited memory. Unlimited in the sense that it would last until you tell it to not last anymore. So this is the last invention we're going to discuss. It goes by the name of long short-term memory, or LSTM. LSTM. I like to call it a transistor because it reminds me very much of a transistor, but it's a continuous transistor. It's continuous, it's parameterized, and it's learnable. So it's a big extension of transistors. So let me tell you what I mean by a transistor. Transistors were invented in the late 40s, and they are used for lots of things. They're the base of all of our electronics, but one of the first basic uses of transistors is as a switch, a binary switch. So we'll call it a transistor switch or a switch transistor, I'm not sure. Transistor switch. And the idea is that there's room here for one bit. That bit could be either 1 or 0. There's input that can set this bit to 1 or 0. There's output, so you can read the value of that bit, 0 or 1. And there's a control signal that gates whether it's a gate. Basically gates whether the input overrides what's here or not. So you can maybe point it to here. Whether you're open to changing the bit or not open to changing it. One manifestation of a switch. What LSTM does is expand on this in multiple ways. One way is that the state of this device is no longer binary. It's no longer 0 or 1. It's a real number, maybe between 0 and 1. So you can think about it as a probability. You can store even things larger than that, but a typical LSTM would be between 0 and 1. So instead of 0 or 1, it becomes a number in the range of 0 and 1. The second thing that it does is instead of the simple operations of replacing the value with another value from the outside, you still have an input here, but it doesn't replace the value, it modifies the value. It adds to the value. Which means you have to take the value that's here and feed it. This is current value. You feed it as a second input. So they are combined together to produce the next value. And you can think, for example, of the sigmoid function as one way of doing that. You add them together through a sigmoid so that it's guaranteed to saturate to no more than 1 and no less than 0. In addition, you have a way of wiping out what's here. But instead of a one-shot wiping out to 0, you wipe it out gradually by multiplying it by some number smaller than 1 so that you're shrinking it. So this goes by the name of forgetting. It's actually erase. It's not forget, it's not passive, it's erase. And it's also not a binary, it's gradual. That means there's some numerical value that comes in here and multiplies the current value. So this is multiplication. This is addition. So of course, if you multiply with 0, you'll get 0 immediately. But if you multiply with something other than 0, you just get a diminishing of the value. And then the last thing you have is the output. You have a gating that controls whether this output is allowed out or not. This is out. The exact details would vary. There are maybe dozens of different variations of LSTMs. I think this is pretty close to the original one. The important thing about it is that the memory is a continuous number between 0 and 1. It could be added to. It could be read out. It could be added to or not. It could be read out or not. It could be pushed towards 0 or not. When it's added to, it's through an additive operation subject to the sigmoid, so that it saturates at 1 if you wanted to. When it's diminished, forget is, they call it forget, but it's really not forget, it's diminishing, because you're not forgetting the whole thing in one go, you're just reducing it. Of course, if you're applying it multiple times, or if you apply a strong signal here, you can effectively forget most of it. If you apply that, that's a multiplicative operation. If you don't apply any forget or any addition, it maintains its value. Now here's the ingenious idea. I put a lot of arrows there. All these arrows correspond to weights. And all these weights are learnable. They're part of the weight of the network. This is why I call an LSTM a transistor, but it's a continuous as opposed to binary, a regular transistor. It's continuous, it's parameterized. And it's learnable. Transistor. The learnable corresponds to these parameters. The biggest breakthrough for processing images was convolutional neural networks. The biggest breakthrough for processing time series data like speech and language was LSTM, because it allowed you to extract and retain global information that could influence your processing further down. Question?
So for LSTM, it's like if you have a fixed range for your forgetting rate, it's just like you should already fix whether you should forget your memory or you're not so bad at not possible.
I'm not sure I understood the question, but this gate doesn't come out of this one, this forget. It doesn't come out of nowhere. It comes out of other units that connect to it. So that means that depending on, this could be hidden units, could be even inputs. So that means that depending on some computation that happens somewhere else in the network, a decision is made whether to forget or not. And that decision is not a binary decision. It could be that for most cases, there'll be a zero signal, a one signal here, which means don't forget, keep it. And for others, there would be close to zero, which means wipe it out. But in the general case, it could be anywhere in between. I don't know if I answered the question.
I think if you have a particular sequence, like at the third frame, you determine like I want to forget, I only want to keep one frame memory, and after that, basically you couldn't trace back to the very first frame.
I see. You're saying that is it the case that once you forgot something, you cannot go back?
I think why you call that long short term, because you only determine whether you want long or short term in one sequence.
Are you asking if it's called long short-term memory because you have to decide whether it's long or short? I don't know. I don't know why they call it long short-term memory. I don't know if I agree with you that you have to decide whether you keep it long or short. I would tend to characterize it as like our own memories. Once you decide to forget it, or once you forget it, you forget it. Well, maybe it's not a good metaphor because sometimes we have forgotten memories that get resurrected. But the point is, once you forget something, it's gone forever. As far as moving forward with your Windows question.
So how do you select the features that you want to recurse on? Or like how many recursive calls do you make?
How many, what?
Like you're saying that it's called recursive in your network. So how many recursive calls would you do to see what is like the subset of the units that you would recurse on? Like how do you make instructions?
What is the subset of units that you recurse on? So how do you decide the topology of a recursive network? The same way you would decide a topology of a feed-forward network, which means with very vague intuition and holding your fingers crossed. I think what you typically would do is you look at the domain and you say, okay, there's some global information here that I think is useful to carry along. What is the dimensionality of that global information? How many units do I think I need to capture that? Somewhat like in a feed-forward network which you all played with, how many hidden units do I need here? Well, I don't know, I'll try a different number. It's very much like the question of hidden units in a feed-forward network in the following sense, that if you gave more units than necessary, it should still work. You will develop a representation in these recursive units that is more distributed. Instead of using just one unit for a concept, you would use more than that. But it would require more data, more training data to still work. If you didn't give enough, you won't be able to learn what you're trying to learn. So it's the same principle. You want it to be big enough, but not too big. Any other questions about DNNs, RNNs, LSTMs? Yeah.
So for the recursive one again, when it's handing down data to the input, is it handing it down to a certain input or is it for every input? I guess I don't see how it ends up ending.
No, it doesn't you cannot hand it down to an input. So let me make that trying to make it a little clear. You can't hand information down to an input because inputs are not changeable. Okay? You can do one of two things. So here we're talking just about an RNN. Here are the inputs. Here's some you can connect from here down to a earlier layer, meaning that the output of this unit for this window goes as input to this unit in the next window over. That's one possibility. The other possibility is, well, it's actually amounts to the same. If you take all of these and you treat them as if they were additional inputs, not to these. These you cannot touch. They are what they are. But I think it will boil down to the same thing. Yeah, it will boil down to basically connecting to the lowest layer. Now, I tried to give you the spirit of this revolution of the last 10 years. There are lots more details. Some of them are going to turn out to be really important. Some of them are going to turn out to be not so important. I think I mentioned to you that this is still an art, not a theory. And that is a very typical thing that happens in machine learning, and I suspect in other areas as well. There are some breakthroughs. Somebody demonstrates that you can do something you couldn't do before. There's great excitement, and people push the boundary of what can be done with it. And this is what we're in the middle of now. We're still pushing the boundary. We're still doing different groups come up with new tricks and new architectures and new ways of training that allow you to learn things that we didn't think were maybe possible, or we didn't know how we would do them. And then a few years later come the theoreticians and try to make sense of the whole thing and try to explain why you were able to do this and not able to do that. In a sense, their life is easier because they only need to explain rather than to do. But on the other hand, it's harder to build a theory for a system that somebody has already built. You don't have a choice of which direction to go. I expect the next 5 to 10 years there's going to be a fair amount of theory. And we would start hitting the limits of what this can do. But we're not there yet. We're not hitting the limits yet. This has happened before. I would say 15 years ago, boosting was a big invention. We didn't talk about it. We're going to talk about it later in the course. And there was a period of a few years when everything was subject to boosting, and it got better results. And then the theory came later and showed what boosting was doing. It didn't invalidate it. It just told us how it's doing it and what the limits are. This is a bigger revolution than boosting, certainly in terms of its impact on the world. We can do things that are closer and closer to what people do, and then sometimes exceed it. It's a very exciting time. I mean, I'm not trying to take away from the buzz of deep neural networks. I'm not terribly happy with any of the books that are out there, but I did find one summary article, not surprisingly, by Jeff Hinton, who I think is an excellent explainer. Jeff Hinton and a few others. I will post it online, and I would highly recommend that you read it. I think it tries to describe the essence of what the revolution is about without bogging down in the details, which is what I try to do here. Okay, I'll see you Wednesday.